we will estimate the certain properties of the hydrogen atom. So hydrogen atom. We shall look at its properties such as size, energy, electric and magnetic field strengths, Okay. And we shall estimate, rather than full force quantum mechanical calculation, we will estimate these properties. So estimate. And estimation, of course, uses uncertainty principle and the Broglie waves. And so we start. First, it is a two-body problem. We have the proton, more or less a classical looking picture, and then we have the electron. So this is a two-body system, and we have already in classical mechanics studied the two-body system. So the energy of the system is the kinetic energy of the proton plus the kinetic energy of the electron plus the Coulomb interaction of between the proton and electron. And this we can change it to the total kinetic energy of the center of mass plus the relative kinetic energy, or the kinetic energy of the reduced mass. So let's write P square over 2 m proton plus m electron plus relative momentum to mu, or let me write m reduced, plus the Coulomb interaction, which is E times, that's for the proton, that's for the electron, times the distance between the two. So this is the distance between them. Here it is, r. So this does not play a role because that means the atom as a whole is moving. So this is the internal dynamics. This is where the interesting stuff is. That's the internal dynamics of the hydrogen atom. First, let's look at this m reduced. How big is that? So we know that m reduced is 1 over m proton plus 1 over m neutron, which is m proton plus m neutron divided by proton, not neutron, electron. Electron, that means m reduced is m proton, m electron divided by, which I can write as P me divided by so this cancels. And this is a small parameter because this is of the order of like 1 over 2000. So it is ME 1 minus 1 over 2000. So we basically neglect. Of course, if you increase the sensitivity of your measurements, of your experiments, then you have to look at the smaller details. But let us look at the dominant aspects of the hydrogen atom. So we simply this M reduced is M electron. So that's how we start. So I am erasing this part, and let me erase these. Remember, we'll look at the size, energy, electric and magnetic fields, and we shall estimate. And we are doing this for hydrogen atom, so I can erase this. So let me write the energy equation. That's P square over 2N. Now M stands for the M electron, basically, minus E square over 4 pi epsilon 0 1 over R. So this is the energy of the hydrogen atom. That's the kinetic of. So this essentially means that nucleus is so heavy, so massive compared to the electron. It sits at the center, and the electron is moving about it. All right. So that's the energy, and we'll try to estimate the energies and the size by using uncertainty principle and the ideas of the Broglie. Well, uncertainty principle says that delta, for example, in one dimension, delta x, delta px is of order h bar, which is h over 2 pi. Now, suppose here is the proton at the center, and the electron is moving about it at a radius r. So, for example, let's take 2 points A and B. And this is the x-axis. xa is equal to 0. The position at A is 0. The x position at B is r, the radius. Therefore, delta x is, I'm talking about the magnitude. So this is about r. Let's look at the momentum. At A, it is going in a circle, so that's the momentum. It is going about it with constant speed. And here it is going with P again, A and B. So at A, PA, I'm talking about the x is P, and PBX is equal to 0. Therefore, delta P is like P. So if we are using this uncertainty principle, PR, P times R is like H bar. R is, of course, is to be interpreted as the most likely whereabouts of the electron. How far is it most likely to be about the proton? However, this is too simplistic a picture, and this was modified by, well, the Broglie improved upon the Bohr's old quantum theory, and he said that if you are talking about the steady states of these atoms, then in this orbit, classical orbit, there must be a full number of wavelengths. So if this is a wavelength associated, there must be a full number of them. Now, in free space, we know that P is equal to h over lambda. lambda being the wavelength. However, in a bound state, what is this lambda? So the Broglie's thing was 2 pi r is n times lambda. Now, of course, n can change, and therefore we better index r with n and lambda with n. So this is the appropriate Rn, this is the appropriate wavelength. So if I divide lambda n by 2 pi, in this lambda n over 2 pi, that's equal to Rn over n. This I will write as lambda slash or lambda bar. Now, if you divide both sides by 2 pi, we can write this as. So, what we are really writing is then, you can localize a wave only within its up to a distance of length equal to its wavelength. For convenience, let's take that to be lambda bar. So P will be, in this case, equal to appropriate for the nth level h bar over lambda n bar. And lambda n bar is Rn over n. So P times Rn over n is like h bar. Okay. So if we compare this highly, very highly simplified approach corresponds to n equals 1. Okay. So let's write that to here. P r sub n over n is like h bar. So I will start taking there. I'm erasing this. So we took n equals 1 and we are looking for the ground state, lowest state. States are counted by this number n. And by the way, there is one more thing. Prn, let me just add this. Prn, which is mv, P is mv, Rn, is nothing but the angular momentum of the electron. So L is equal to nh, which is the Bohr's quantization principle. Bohr's quantization principle. So we are basically using uncertainty principle, the Broglie's hypothesis, and Bohr's quantization principle to have these estimates about the hydrogen atom. So we start with n equals 1. So we are starting with that. So delta P is of order P. Delta uncertainty position is of order R. So this is basically R1. But R1 is usually referred as R0. Most of the time it's called A0, the Bohr radius. I will use R0. So we are coming to here. We now insert. P is with n equals 1. P is like h bar over r. Namely, the uncertainty in the momentum is h bar over the uncertainty in the position. So we write this h bar square over 2m r square minus e square over 4 pi epsilon 0 1 over r is equal to e. All right. So e is a function of r because all these things are constants. This is the magnitude of the electronic or the proton charge. 1 over 4 pi epsilon 0 comes because we are using MKS system. H bar is Planck's constant, m is electron mass. So the only variable is r. That's E of r. All right. Let me just write this one. P r n is equal to r sub n and h bar, and then erase the rest here. Let's look at how these things behave with R. This is the kinetic energy term. This is the potential energy term. Sum of them is the total energy. Now, 1 over r square at small distances dominates over 1 over r. So at small distances, this is the term that is dominating the energy. So if it is positive, this is r, and it goes like this. So this is the kinetic energy. How about the potential energy? This also goes to negative infinity as r goes to 0, but this is the dominant one. This is dominant at larger distances. So this is the potential energy. So as r approaches infinity, it goes to 0 from below. So it is like this. This is the potential energy. And if we add them, that's equal to total energy. So let's look at how the total energy behaves. For short distances, the kinetic energy term dominating, it is like that. For long distances, potential energy is dominating, and it is like that. It's obviously, and these 1 over r square and 1 over r are continuous functions, so it's obvious that this term will come down, and at some point will change, will stop going down and turn around and go up. So it is like that. So there is so this is E of r. So there is a minimum of this energy. Let's say it happens at position r0. So we will say r0 is the, well, that will determine the size of the hydrogen atom. Or let's do it like this. Let's say, let's define a dimensionless parameter, x r over r0. So if we plot p of x versus x equals r over r0, so it is similar to that. Like this. So the minimum is at x equals 1 by construction, except that we don't know what r0 is. So let's write energy in terms of x. E of x is h bar square over 2m. R is x times r0, so it is r0 square times x square minus e square over 4 pi epsilon 0 r0 1 over x. That's it. That's E of x. And well, E is energy. X is dimensionless. Therefore, the rest of these terms carry the dimension of energy. I think if this point is clear, I'm erasing it because we don't have blackboard space. So this is gone. Just to remind us, x equals 1 is the minimum. So let's write this as a over x squared minus b over x. That's e of x. And we know that the derivative of x, e of x at x equals 1 is 0. dE dx, that's equal to minus 2a over x cubed plus b over x squared. And this is at x equals 1. At x equals 1, which is minus 2a plus b, that is equal to 0. So b is equal to 2a. When it is minimum, the strength of the here. This is B, this is A. Strength of the, when x equals 1 at the point where E is as a minimum, strength of the potential energy is twice the strength of the kinetic energy. All right. Now, still, we know that we have a minimum at x equals 1, but we don't know what R0 is. Okay. However, we have this condition. B over B is equal to 2a. All right. So B over A, let's look at B over A. That is h bar square over 2m r0 square. Nope, it's the other way around. E square over 4 pi epsilon 0 r0 divided by h bar square over 2m r0 square. That is equal to B over A is 2. Right, from here, B over A is equal to 2. So this is equal to 2. I'm erasing this part. So R0 comes up from this division. E square over 4 pi epsilon 0 R0 divided by h bar square over 2m is equal to 2. So R0 is equal to 2 times h bar square over 2m divided by E square over 4 pi epsilon 0. So 2's cancel. It is h bar square over m E square over 4 pi epsilon 0. Now we have to evaluate this numerically. Now in physics, every problem defines its own scale of parameters, and you use units appropriate for those problems. For example, if you are talking about distances, if you are measuring how big your room is, you talk about in meters. But what is the length to a star? Measuring it in meters doesn't make sense because so many meters. So instead we use light years. Or if you are talking from Istanbul to Ankara, then we measure it in kilometers. So we have to we better use the appropriate units and calculation methods appropriate for the hydrogen atom, or in general atomic world. So no physicist really memorizes the how big H is in MKS, or M is, or E square, or epsilon zero. We use we make life simpler in atomic physics by such combinations. For example, H bar C is, this is not exact, this is approximately electron volt times angstrom. So the appropriate energies are electron volts, and the appropriate size is 1 angstrom. All right. And then E square over 4 pi epsilon 0 over H bar C. This is 1 over 137, which we will use as 140. We may take it also 1 over 150. And the mass of the electron is 1/2 10 to the 6 electron volt, namely 1/2 MeV. All right. So we shall use these to approximate any physical quantity related to the hydrogen atom. So let's use this. R0 equals, I multiply by C square, divide by C square. So it is H bar square C square over M C square times E square over 4 pi epsilon 0 equals, if you look at here, I have E square over 4 divided by H bar C. So I take 1 H bar C down. So this one remains. I have MC square. Then I have E square over 4 pi epsilon 0 divided by H bar C. And now I plug in from the table. That's equal to 2000 electron volt angstroms divided by MC square. That's 1/2 10 to the 6 electron volts times 1 over 140, let's say. So electron volts cancel. We are left with angstroms. Then we have to do this numerics. 4 times 140 times 10 to the 3 divided by 10 to the 6. This is 560 times 10 to the minus 3. So this is 0, that's angstrom. That's 0.56 angstrom. So in the ground state, hydrogen has this radius R0. Let's write this here. R0, which is H square over M E square over 4 pi epsilon 0, right, is 0.56 angstroms. Well, if you put the correct numbers, it changes only little to 0.53. But let's keep it with 5.6 because we just want to estimate. Now, I am erasing this part. I'm writing this energy U of x again. U of x was A over x square minus B over x. And this is A, and this is B. And B is equal to 2A. B is equal to 2A. And A is a positive quantity, H square over 2m r0 square. So let's call A, let's measure it in energy units, epsilon. I'm erasing this part. E of x is epsilon over x square minus epsilon over x. And we know that E equals, at x equals 1, that's the minimum of the energy. So when you put, this is 2 epsilon. Where is it? B equals 2a. So if you put x equals 1, this is epsilon minus 2 epsilon. That's equal to minus epsilon. I'm erasing this part. So let us write for E as minus the binding energy. And this is minus epsilon. This is E minimum. Therefore, epsilon is the binding energy. And how big is this binding energy? Epsilon, which is A was h bar square over 2m r0 square. Now we put in the, again used that table. This is h bar square c square over 2 mc square times r0 square. That's equal to 2000 electron volt angstroms, 2000 electron volt angstroms divided by 2. mc square is 1/2 MeV. 1 MeV is mega electron volt. That's 10 to the minus 6 electron volt, 1 million electron volts. So it is 1/2 10 to the 6 electron volts times r0 square. So let us write r0 as 1/2 angstrom. This is 0.56, so this is 0.5. Anyway, we are doing estimation. So it is 1/2 times 1/2 angstrom square. So let's see what does this say. 2's cancel. 10 electron volts cancels that. Angstrom squares cancel. All right. I have 10 to the 3, 10 to the 3, 10 to the 6. So that goes. So only the 2's. 2 times 2 is 4, multiplied by 4, something like 16 electron volts. So if you put the correct numbers, this was not 1/2, but 0.56, etc. This was not really 2000, a bit less than that, etc. If you plug in all these numbers, the correct value is epsilon is 13.6 electron volts, and which is called 1 Rydberg. 200 Rydberg. All right. So let me just summarize. I am erasing this part. Let me just copy the result here. Epsilon is simply the binding energy in the ground state, which is h bar square over 2m r0 square. And that's let's use that 13.6 electron volt. We estimated like 16, but it's okay. It is very close. So I'm erasing all this. Let us summarize so far. What did we do? So if this is the electron trajectory, for n equals 1, we took one wavelength. So if you just open it up, for example, this is 2 pi r0. We took one wavelength that fits to here. So never mind my drawing, but it is something like this. So this is the up part, this is the down part. So one wavelength fits in. And the size of the atom in the ground state is 0.5 angstroms, half an angstrom. And the energy, binding energy is negative. And E is minus EB, which is minus 13.6 electron volts. Now, perhaps we should pause and think about this a little bit. 1 angstrom is 10 to the minus 10 meters. That's the definition, meters. So it is very tiny, but that's the length scale of the hydrogen atom. It's a tiny thing, but its binding energy is 13.6 electron volts. All right. Now, what is the physics here? The physics is that as the electron moves away from the proton, this term drops and you have a strong electrical attraction, Coulomb attraction, and it attracts the electron toward the center. As it comes toward the center, the kinetic energy term dominates and electron cannot penetrate and pushed out. So there are two effects. In a sense, hydrogen atom, I am repeating Professor Weisskopf's words in some sense. H atom is the balance between the attractive, between the electric Coulomb attraction and the quantum pressure out. Quantum pressure out. So this quantum pressure is this term, namely as electron approaches the nucleus or the proton, it gains this kinetic energy and pushed out. That's the quantum pressure. If it moves away, there is the Coulomb attraction, and the stable situation of the hydrogen atom is the balance between the two when the energy is minimized. This occurs often in physics. A good example, another example, is the stars. For example, our sun is a star. Here is the star. All right. The star is the balance. We can use the, instead of Coulomb attraction, there of course the gravitational attraction. Gravitational attraction. So that's what pulls the star toward the center. Every sphere pulls the material outside toward the center, but there is a pressure out, and that is the thermal pressure out. Thermal pressure out. So a star is the balance between the gravitational attraction and the thermal pressure out. Okay, so that's for the star. For example, a similar thing happens also in your kitchen. For example, here's suppose you are boiling some water. Here's your fire. So it's bubbling. So if you just put a lid, the vapor will push the lid up, but the gravity will pull it in. Gravity. So sometimes you hear dingle, dingle. If it goes up, gravity wins because this pressure has dropped. If it moves in, pressure increases. So I just wanted to indicate the idea of this balance, which is exactly the same there. Okay. One more statement. Gravitational attraction is always there, and here the Coulomb attraction is always there. So these are the attractive forces. What about the balancing forces? Quantum pressure, by the very nature of physics, the uncertainty is there, and it's always balancing the Coulomb attraction. What about this thermal pressure? Well, to create thermal pressure, you have to burn something, and the star burns hydrogen. At the core there is hydrogen, for example, like our sun. It is burning this hydrogen. But if you ever sat down next to a fireplace, you know that finally the wood finishes, it's all burnt. You have to put in more wood. Now, here we have to supply more hydrogen, but where is that? Hydrogen has turned into heavier elements by fusion. It has become helium, so you have to start burning helium. I am saying that this thermal pressure cannot be kept indefinitely, because you keep burning your fuel and gravitational attraction is there, but thermal pressure out, well, it is not there all the time. So if it's a very big star, let's say 20 times the mass of the sun, you can burn it finally up to iron, but you cannot burn heavier elements or including iron as well. Why not? Because by fusion you cannot get any more energy. So thermal pressure, the source of thermal pressure is out. So what happens? What happens is that star collapses, and then you have this star dies with as a supernova, and much of the star is blown away. It's a terrific process. The whole star is detonating, and at the center you will be left with the neutron star, or if the star is massive enough, with a black hole. All I'm saying is that the same game is played in the stars, except that the source of the pressure out in the star is a thermal source, and thermal source requires a fuel, and this fuel finishes. Whereas, so for example, our sun has burned its hydrogen for 10 billion years, 5 billion years have passed. It has 5 billion years to go with burning hydrogen. So it's on billions of years for the stars. But what about the atom? Well, this effect is always there, and as long as the proton lives, the atom will live. This has no time limit. Now, there are some theories, supersymmetric theories, and they predict some lifetime to proton, and experimentalists put a lower limit, and that limit is about like, I'm talking about proton lifetime, and that proton lifetime is like 10 to the 34 years. Now the age of the universe so far is something like 14 billion years. 14 billion years. Say it's 10 to the 10 years. So for protons, you have 10 to the 24 years. You have to multiply the universe's age by 10 to the 24. So it is 10 times the universe age times another 10 times another 10. Okay. So for all practical purposes, for our purposes, hydrogen is stable, and all atoms are in their ground state are stable. And okay, I'm erasing it. What about the all right, this is our star. Well, we just did one wavelength, so with a bad drawing it is something like this, namely one wavelength. What about 2? So P times R2 is equal to 2 times H bar. So you see, essentially the mathematics of it is that H goes to like going to 2H bar. So let's check with R0. These are all constants. So R2, I'm calling it R2 because that's n equals 2. For n equals 1, we use somehow R0. R2. So R2 will have 2H square. So it is 4R0. 4R0. It is 2 to the 2 R0. And how about energy epsilon? So this is epsilon 1, epsilon 2. Let's look at here. H goes to 2H, but so we can write this thing as 2H bar square over 2m, and R2 is 2 to the 2 R0 square. That's equal to, so 2 to the square of 2 is 4. This is 4. Square of 4 is 16. So it is 4 over 16 epsilon 1. So it is epsilon 1 over 4, or epsilon 1 over 2 to the 2. So that's the next state, namely it will, we will find the electron. So if this is the thing, so if you open it up, there are 2 wavelengths. 1, 2. Okay, and then you wrap it up, so it becomes a figure like this. What about n? So H goes to NH bar, H bar goes to NH bar, and Rn goes to, from here, NH bar square, so it is n square I R0, and epsilon n. From this formula, n square I get from here, but n to the 4th from here, so it is epsilon 1 over n to the 4th times n square, so it is epsilon 1 over n square. So these are the sizes of the steady states of the hydrogen, excited states of the hydrogen, namely the radius grow by n square, and energy is reduced by n square, and n is 1 to all the way to integers. One last comment in this regard is let us appreciate the binding energy of the hydrogen. We said epsilon binding, epsilon 1 is like 13.6 electron volts. Well, okay, it is stable and all that, but it is how stable it is. You know, if you just tickle the hydrogen, can you ionize it? So let's just look at these numbers. Kb, for example, 1/2 mv square average is of the order of kBt, and at room temperatures, this is like 1/40 electron volt. You can imagine 13.6 electron volt is a tremendously stable structure at room temperature, because kB T room is 1/40 electron volt. kB T ionized is like 13.6 electron volts. Let's divide kB, electron volts go away, and T ionized equals T room times 13.6 times 40. T ionized comes here. You are dividing by 1/40, and 40 flips over to the top. So T room is something like 300. So this is like 1.36. Let's make it 400. So here you have 10 to the 4 times, this is 12, and this is perhaps something like 15. All right, 1.5, 15. So 150 Kelvin. Can you imagine? To ionize the hydrogen, you have to put it into an environment with such great temperatures. That's why atoms are so stable. That's why, for example, the oxygen molecules that we need to breathe in air, they are moving roughly with the kinetic energy 1/40 electron volts. They collide. The energy is not enough to ionize and distort the oxygen molecule. It remains as an oxygen molecule. So we continuously breathe this air with oxygen molecules intact. So that's the quantum stability. One last word about this uncertainty. Uncertainty is not making the physics uncertain and, you don't know, it is completely uncertain. No, it's not that. Uncertainty principle makes certain that atoms are stable. Uncertainty principle makes it so that atoms have stable structures. That's how we can live with stable structures of atoms and molecules. And look at the planetary systems. If two planetary systems had collided, it would be a big mess. They would not scatter off as billiard balls. We owe it to this binding energy. All right. So we have discussed in the hydrogen atom the size of the atom in its nth state and the energy of the atom in its nth state. Next, we shall look at the electric field and magnetic field in the atom.